Hello, welcome to a new virtual tour of the European Southern Observatory, or simply ESO, its acronym. So my name is Farid Char, and I am going to be your guide during this trip to ESO Paranal Observatory. So just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the observatory since 2010, and I am also working for an astronomy center of University in Antofagasta, and I have been working with the observatory for a long time, so um, I am familiar with the place we are going to visit today. So if I want to be with you during these virtual visits and bring astronomy directly to your home or wherever you are. So please remember, you can send your questions or comments during all this streaming. So I imagine you have some questions already. So you can leave your questions or comments in the comments section of this broadcast on Facebook or YouTube. So we are going to allocate some time to answer your questions later. Okay. So okay, we are going to start with this virtual experience, and in order to understand better the organization, I am going to talk a little bit about ESO. So I am going to show you something first. I am going to show you a picture of the member states. So in this picture right now, you can see that ESO is composed of 16 member states. In this picture, you can see also that Australia is there, but in this case is a strategic partner, and Chile is the host state. So the headquarters of ESO are located in Germany, okay, in Garching. So from the 1960s, and with those objectives in mind, okay, so ESO has chosen one of the best places for astronomy. In this case, the Atacama Desert in Chile. So during this period, in the 60s, Chile started Chile started several site explorations in order to attract international observatories such as ESO to our country. So as a result, Chile offered its territory, and ESO did choose the more suitable areas. So the mission of ESO is basically to design, build, and operate astronomical observatories. And why? Why exactly? Well, to enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. So right now, I am going to show you a picture with the three observation sites of ESO in Chile. Give me a moment, and I will show you the places right now. So these are the main observational facilities. So in first place, we have the Shahnan-Tor Plateau. This is the site of the ALMA and APEX radio telescopes. ESO is part of these places for radio astronomy, alongside other international partners. In addition, south of the Atacama Desert, at 2,400 meters above sea level, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes, such as the NTT or the 3.6 meter ESO telescope. And in this case, in the 3.6, this one is using the HARPS instrument, and this one is an exoplanet hunter. So it's very, very important. And finally, we have the place of our visit, Paranal Observatory. This ESO observatory is the home of the Very Large Telescope, or VLT. This is the most advanced visible light telescope on Earth. So in the next few years, we will also have the Extremely Large Telescope, or ELT. So this will be the biggest visible light telescope on Earth. And also near there will be another important facility, the CTA, because that will be an array of different telescopes, but in this case, they will be focused on capturing gamma rays. Okay, so now we have a better picture. So we are going to travel right now to the Paranal Observatory. So I am going to show you a simulation going to this observatory. So this is something like a like a virtual uh, approach to Paranal over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital Santiago, and specifically about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Taltal, the closest city. So now we are going toward the mountaintop of Cerro Paranal, and this place is located at 2,600 meters above the sea level. This mountain belongs to the coastal range, and despite its altitude, it's located at just 12 kilometers from the coast. Now, where's the ocean? Well, the Pacific Ocean is located below of the cloud cover that you can see in the horizon. But why those clouds? Because if right here you see the sky is so clear, dry, and lonely. Well, this is because of the influence of the Humboldt current. And this is a cold current near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level, keeping below the cold, humid, and basically bad air for astronomy. And above the layer, instead, we have the hot, dry, and less dense air. So this is something like the good air for astronomy. The clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing the 2,000 meters above sea level. Now, we have other natural barriers around this area. About 200 kilometers to the east, we have the Andes Mountains, with very high mountains, more than 6,000 meters above sea level. So this is another natural barrier blocking the clouds, in this case, coming from Argentina and Bolivia. So the main result is this landscape. So this is basically a place with an average of more than 300 clear nights per year, with very clear and transparent atmosphere, making it ideal for observing the night sky. Also, here we are far away from artificial light sources because of human activity. I mean, light pollution. So overall, this is one of the best places on Earth for astronomical observations. Okay, right now I am going to change the view to show you an even closer look to Paranal. Okay, so as you can see here, this is not an ordinary mountain, and now we can see the different telescopes and structures in the mountain. We are at the summit of Cerro Paranal. Now, Paranal in the Quechua language means whirlwind, possibly, possibly because of some whirlwinds forming in the desert. However, as I told you already, the atmosphere here is extremely quiet. This observatory is like a true oasis. So you will see how in one of the driest deserts we have a lot of life, and of course we have a lot of science. Okay, so right now I am going to change the view to show you the summit of Paranal. So let me a moment and I will show you right now the mountaintop. Okay, so in front of us we have the Very Large Telescope, or VLT, its acronym. Okay, so if you see the amount of buildings, I mean 4 giant domes and other 4 small and rounded ones, it is clear that the Very Large Telescope in fact is not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. So let's take a closer look. Here you can find the 4 unit telescopes, okay, or UTs. I mean the big ones in front of you. Each one has a primary mirror of 8.2 meters in diameter. The giant ones right here. But we have other telescopes. We have some small ones like this one, and these ones are the auxiliary telescopes, each one with a primary mirror of 1.8 meters of diameter. So we have 4 auxiliary telescopes. Here we have one, we have another one, we have this one, and we have the last one here. Now, coming back to the main telescopes, the unit telescopes or UTs, well, each telescope, each UT, has a name in Mapudungun language. So this is basically the language of the Mapuche culture, natives from central south of Chile. So in first place, we have Antu right here. Antu means sun. This one is Cuyen, and Cuyen means moon. This one is Melipal, and Melipal is Melipal means 4 stars, but this is related to the Southern Cross constellation. And the last one is Jepun, and Jepun is a word is a reference to the planet Venus. So this is basically the meaning of the origin of each name. And as I told you already, the other telescopes, the closer ones, the small ones, are the auxiliary telescopes. Something important about them is that they are mobile and they can be moved using a rail system. So if you see here, we have something like a rail, you see, and we have something like stations, okay, stations on the ground. Actually, we have 30 stations, so we have 30 different positions. So we can change the configuration of the telescopes on this platform. So the telescopes can be in different configurations. I mean, more compact or more extended. And this is intentional because they were specifically designed to work all together as a single big telescope with a variable diameter. And in this case, this system, this this group of telescopes will be able to reach up to 200 meters. I mean, we can simulate a virtual telescope up to 200 meters. But to understand this technology, this technique, I will show you an animation, a short animation, to let you know more about this technique that is called interferometry. This is the name of the technique to combine light from several telescopes. So we are able to observe much more specific details if you compare this with the individual telescopes. So thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during this travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. Okay, so this animation is trying to show you how we can combine light from several telescopes. We can combine the 4 small ones or the 4 big ones. Okay, so now we are going to come back to the tour screen. And now you will have the opportunity to visit one of the telescopes. So we are going to take a look to the inside, and we are going to visit specifically this one. We are going to visit the UT3 or Melipal. We can't enter all the telescopes, but don't worry about that, because the four ones are identical in size and shape. So the only difference are just the instruments inside. Now you can know more about the instruments, of course, on the ESO website. Okay, so now we are going to enter to this telescope, the UT3, and here we are. So what can you see? This is a giant telescope, of course, right? Right now we are on the last floor of the telescope at the same height of the main mirror in front of us. This mirror has 22 tons with 8.2 meters of diameter. I will show you a close-up here. And only 17 centimeters thick. The mirror was created from a ceramic and flexible material that is called a cerodur. By the way, the surface is a very thin layer of aluminum. So this is basically the reflective material to reflect light from the stars. Now, when you are observing the stars at night, of course, we have to point the telescope to different positions in the sky. And you need to consider that this mirror, the main mirror, is heavy. It's heavy, and by the way, the mirror is concave. It's like a spoon, let's say. So, of course, we need to be very careful with this mirror, and we need to take in mind that because the mirror is so heavy, we need to prevent any possible damage, and we need to prevent any, let's say, possibility that the mirror can break. So how can we point this telescope to the sky and move to different positions without breaking it? Well, we are going to show you this mirror from another angle to explain a little bit about that. I will show you the mirror, I mean the telescope from this area, from the platform. So I am going to change the view. Now we are, as you can see, at this level. It's like the telescope level, and from this position you can see that the mirror is mounted over this white cell. Okay, so this is a cell supporting all systems assisting the mirror, including something called active optics. So what is that? I am going to show you now. I am going to do a close-up to show you this kind of gray boxes. You see, we have something here like gray boxes. So the gray boxes are something that we call actuators. They are a kind of piston, and we have 150 in total, and they are controlled by a computer. Now, they are acting on the mirror during the observations in order to keep the optimal shape of this concave mirror, the concave surface. So otherwise, it could suffer deformations just because of gravity or physics. So those deformations, even imperceptible in a first view, could be critical in the result of the observations. Now, how the telescope is working all together. I mean, how the telescope can receive light, and how we can process this light. I will come back to the mirror, to the top floor, to show you another animation in order to explain that. So let me show you very quickly an animation here to explain how the telescope is working at night. So the first step, of course, is to open the doors. Of course, this is exaggerated in this animation. So the light is going to impact first in the primary mirror. Because the primary mirror is concave, the light will be concentrated and reflected to a secondary mirror in the top, as you can see there. Then the light will be reflected again to a tertiary mirror in the middle, and the light will be reflected to one of the instruments. It could be the instrument in one side, for example, with like this red box, or the other instrument in the other side, like this blue box, or even we can even lift the tertiary mirror, so the light can go directly to the bottom. So we have another instrument in the base. So basically we have three different instruments, and we can take advantage of three different instruments per telescope. Of course, not at the same time. We can use only one instrument at the same time. So, but the important thing is that we can use different instruments to observe different things and with different specifications. So this is basically more or less how the telescope is working at night. Okay. Um, so in the end, all the instruments they are going to convert the physical light into a digital signal, and this digital signal will be transferred over fiber optics to a control room. So in this control room, we have the astronomers working at night. They are not here at night. This place is completely in darkness at night. So during the day, we have engineers working. For example, in this picture, you can see some engineers. They are doing some kind of maintenance, So basically, during the day, the engineers are working, doing maintenance, fixing problems, doing calibrations. So basically, they are preparing the telescope for the next observation night. So during the day, the work is for engineers, and during the night, the work is for astronomers. This is more or less what happens in a professional observatory. Okay, so with this explanation, I am going to finish this virtual visit to Paranal, because actually our next stop will be the control building. I mean, the place, the workplace for the astronomers. So we are going to come back to the platform, to the main platform again, in order to visit the control room in a few moments. Okay. Um, by the way, the control building is located in the mountaintop, but it's not at the same level of the telescopes. The control building is located there. So as you can see, it's like in a lower level. You see, I will show you the control building from the opposite side. So you can see that it's this building. It's a big place, of course. And the last floor is for the astronomers. We have the control room there. Okay. But before this visit to the control room, I am going to check very quickly in case we have some questions from our virtual visitors. So, for example, I can see right now that we have, of course, several greetings. We have a person from Amsterdam. We have a person from Denmark. Thank you for coming again. We have a person from Milano. So we have a lot of people visiting this virtual experience, and we have a question here from Paola Flores. She's asking if this platform is available for general public. Yeah, I mean, Paranal is available for public visits. And in order to visit Paranal, you need to do an online booking on the main ESO website. Okay, for example, well, if you are visiting from Chile, you can go directly to the ESO website, eso.cl or eso.org, and you can find a section that is about the public the visits. And you need to do an online booking. You need to specify how many people, and we have visits all Saturdays. We have two available times, 10 a.m. or 2 p.m. And you need to consider that the travel time from Antofagasta, that is the closest city, is about 1 hour and a half. So it's always better to consider 2 hours of driving time. You need to arrive at your own transportation, but the visit is completely free, and the visit takes around 2 hours and a half. So yeah, you can visit this platform, but it's only during the day. It's a daytime visit. Okay, so I am going to check if we have another question. Okay, we have a question here about the aluminum surface oxidation. Okay, this person is asking about surface if we have some kind of loss of refractivity or something like that. Basically, yeah, I understand you. Your question is about basically what happens with the surface of the mirror. And in order to answer this, I will answer better what happens about the maintenance of the mirror, because yeah, we need to do something on the mirror in order to keep the quality of the observations. So basically we have to clean the mirror, okay? We have two ways to clean the mirror. Once a month, more or less, we need to do an easy maintenance, let's say. This easy maintenance involves to rotate the mirror a little bit, and a couple of engineers, they are going to spread a carbon dioxide snow. This is something like a foam, and this element is basically to remove dust. Okay, this is the main purpose of this element, is to remove dust, because we are in the desert, we have dust in the environment. So this is something like a non-invasive system to keep the mirror more or less clean. Okay, but we have another way to clean the mirror, and this is more complex, and this is involving a more important action on the aluminum surface, because every 2 years we have to remove all the mirror from this telescope. We need to physically extract the mirror to the outside, and in the outside you will see, for example, it's visible in this picture. You can see a yellow structure here, right? So you need to extract the mirror, you need to put the mirror there, and at the ground level we have a vehicle. So this vehicle is going to receive the mirror. Okay, we have something like bars here. So we have to drop the mirror very gently, of course, in the vehicle. The vehicle is going down to the base camp, and we need to move the mirror to another facility, that is the mirror maintenance building. So in that place, you need to remove the aluminum layer with some chemicals, and you need to put a new one. So in this case, when you put the new layer, it's more or less like like change all the mirror. You see, because you need to replace the old surface, and the new one will look, of course, like a new mirror. So all this process takes about 3 or 4 days, and when the mirror is ready, we need to bring the mirror again to the platform. We need to lift the mirror, and we need to reinstall the mirror in the telescope, so the telescope will be ready again for observations. So that's the the issue. Um, eh, so that's why the Paranal Observatory has been able to work for more than 20 years. Um, but you need to basically understand that we are replacing all the aluminum layer. Okay, so the mirror, the main structure of the mirror is the same, but the aluminum layer has been replaced many times over all these years. Okay, okay, we need to continue now. So later we are going to continue answering more questions in case we have more questions, because we need to continue with the tour. And now I am going to show you what happens in the control room. So in the control room, oh, and by the way, thank you very much for your questions during this time, and thank you for your greetings, because we have a lot of people visiting today. I am going to show you now the control room. So I am going to enter here. Oh, sorry. I'm going to enter right here. And here we are. So this is the control room. Do you see? The control room is more or less like any office space. You see, it's not something too futuristic. It's just an office space. But basically, um, we have several separated workstations. we have workstations for each telescope. For example, this workstation right here. This is specifically for the Melipal telescope, you see? So only operations with Melipal are from here. We have several computers. You see, we have some computers, we have some people here, so they are working specifically on this telescope. Now, just in front, in the opposite workstation, this workstation belongs to UT4, Jepun. So only operations with Jepun are from here. So it's the same situation. We have several computers for different purposes, and we have some people working there. Okay. But again, this is like an office space. It's nothing so too futuristic. But of course, they need to work all night from this place. Now, if we continue through this virtual corridor, I will show you another workstation here. This is the workstation 4 and 2, UD1. And in the opposite direction, we have the last station, let's say, for Cuyen. So essentially, all the telescopes, instruments, and systems explained before are controlled from here. So during the day, engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. I am going to show you this workstation more closely. And I want to let you know that each night we have a telescope operator and an astronomer per telescope. For example, in this picture, I can tell you that this person is a telescope operator. Okay, the telescope operator is in charge of the technical details and the movement of the telescope. So he's something like the pilot of the machine. But this person is usually working alongside an astronomer in the same in the same workstation. So let's say that this person is astronomer. So the ESO astronomer is in charge to direct the scientific observations, and this person will decide the next steps. So he is more like the co-pilot. And the observations, of course, are performed by experts from ESO for scientists from all the planet. So in this picture, to summarize, you can see different terminals for different purposes. For example, the pictures from the instruments, some meteorological information, so different things. And the people here is working all night. Okay, so this is what happens here. It's not a lot of information actually. You need to understand that the people here is working all night. So they are working during the night and they are sleeping during the day. So now we are going to come back to the previous screen. I want to show you the VLT platform again. And because now you have a lot more information about the observatory and the people working here, now I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean, La Silla, Paranal, and Chajnantor. So scientific staff from different countries are using the ESO telescopes to study some objects near to our home solar system, but also others located in the more distant places in our universe. So now we are going to explore a list of the top 10 discoveries from the ESO sites so far.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam, or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, well, this was the top 10. Of course, very, very interesting. But we have just one more thing. We have something like a bonus track. So let me show you very quickly. This is about an somewhat old story, but of course, very, very interesting. It's about some news about the first picture of a black hole. So the Event Horizon Telescope, or EHT, its acronym, an array of 8 ground-based telescopes distributed on the planet, working as an international collaboration, was able to achieve the first direct evidence of a supermassive black hole. So the picture will reveal the black hole in the center of Messier 87, a massive galaxy in the close galaxy cluster in the Virgo constellation. This object is located 55 million light years from Earth, and its mass is about 6,500 million times the mass of our Sun. Okay, we hope you liked the top 10. This was only a fraction of the discoveries thanks to the ESO telescopes and the scientific staff behind them. Now we can continue, and from the platform again, I am going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. So as you can see in this beautiful picture, the sky is almost completely dark with the last traces of light from the twilight. The moon is below the horizon and the sky is full of stars. So the first thing I want to show you is a very nice constellation here just above Antu. This is a very popular constellation. This is Orion. You see, I am going to do a close-up. So this is Orion. In the mythology, it represents a hunter. You can recognize Orion because of those three stars, somewhat aligned, representing Orion's belt. And inside of Orion, we can see another interesting object. I am going to do another close-up. This is the Great Orion's Nebula. Okay, so this is a very popular object for amateur astronomers. This is a star-forming region, and it's beautiful, of course, when you look through a telescope. Okay, so we are going to move a little bit to change the position. We are going to show you the brightest star of the night sky, this one. This one is called Sirius. This star belongs to the Canis Major constellation. This constellation represents one of Orion's hunting dogs. Okay, so the Canis Major constellation is here, and this is the brightest star in the sky. So we can say that the constellation here is connected in the mythology to Orion. Okay, to this constellation right here. Now, if we come back to Antu, the telescope next to Orion, we have another important object just next to Antu. So let me do a zoom in. And this object right here is an open cluster. This is called the Pleiades. This is an open cluster located in the Taurus constellation. Now, the majority of those objects are visually close to a specific area, very populated with stars. So if we look from this perspective, you can see that we have a more concentration of stars here, right? Um, Actually, we are looking at one of the Milky Way arms, and this is our galaxy. And our sun is only one among hundreds of millions of stars. So during the winter, in the southern hemisphere, we can see the center of the Milky Way actually, and this is another area full of stars between Scorpius and the Sagittarius constellations. And you can see all this area from this hemisphere, from the southern hemisphere. Okay, so now we are going to move a little bit to show you another section of the sky in order to find two spots in the night sky. I mean, those ones. So what is this? Those spots right here are the Magellanic Clouds. Up there is the large Magellanic Cloud, and down there is the small Magellanic Cloud. But they are not actually clouds, of course. They are galaxies with an irregular shape, and both of them are visible to the naked eye in a clear night like this one. So this name, the Magellanic Clouds, refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, the people actually had no idea about what a galaxy is. So that's why they recorded those objects like clouds. Now, another important area right here is the smallest constellation in the sky, the Southern Cross. I am going to do another close-up so you can see the Southern Cross right here. As you can see, the cross is tilted right now. So this is an easy constellation to find in the sky. This is only visible in this hemisphere, and this is a good guide to find the South Celestial Pole. So this is a projection of the Earth's South Pole. So during the night, the stars appear to revolve around this point. So to find this point, to find the South Celestial Pole, and because we don't have any bright star near there, we need to do something using the Southern Cross, actually. We can extend, in our imagination, the longer stick of the Southern Cross. So we need to do that more or less like 4 times and a half. So we can do that right now. We can project 1, 2, 3, 4.5, and more or less like here, we have the South Celestial Pole. So this area also, if you try to well, to look at the horizon toward this direction, I mean, if you look toward this point, you are actually looking at the south cardinal point. So this is something like interesting way to find the cardinal points if for any reason you are lost in the desert. So this is what happens here. This is just a quick view of the sky, of the southern sky. And now I am going to return to the main platform because now we are approaching the end of this virtual tour. So this is your opportunity to take a last look to the sky, to the night sky. Please remember that we can do this only using a virtual tour because the in-person visits are only during the day. So now I am going to change the view to return to the main platform. And now we are reaching the conclusion of this visit to Cerro Paranal. We are going down now to another place. We are going down to the 2,400 meters in order to visit a very special oasis. So we are going to visit the residence of Paranal. But in order to do that, we need to change the view and we need to move to the base camp of the observatory. So the base camp is actually in the, let's say, in the base of the mountain. So we need to go there right now. The base camp is located here. So let me show you very quickly. So this is the base camp of Paranal. As you can see, something like a mini city with all the necessary facilities for the workers. So for example, in this place, we have some rooms for contractors. We have we have the mirror maintenance building. So we have a lot of facilities, but I just want to focus on a very specific and beautiful place that is called the residence. It's this place right here, because the residence is the place where the ESO staff can stay and rest. So the residence is the home of the ESO staff when they are working in the desert. And as you can see, we need to use this ramp to do access. Okay, this is something like the roof, this kind of let's say dome. But this is not this facility is not underground. It's not an underground facility. This place is just taking advantage of the shape of the land. So in the opposite side of this residence, it's just a regular building with some walls and with many windows. But from this side, we need to access using this ramp. So we are going to enter right now. And here we are. So you can see that the workers in this place can enjoy a more humid air, and they have a lot of nice facilities. So, for example, we have a swimming pool, we have green areas, and we have, of course, a much more comfortable um, place because the people here are working in a shift system. So they usually stay 7 days here and 7 days at home. Some people lives in Santiago, so they need to come to the observatory for a few days and then they come back. And some people also lives in Antofagasta and so on. Over there, we have the restaurant for all the people working here. This is something like a lobby. This is a reception. So this is very similar to a normal hotel, but it's only for the staff. It's not for tourism. But anyway, it's a very beautiful place. And with this beautiful view, I am going to conclude the general explanation of Paranal. And now we have some with some last minutes to explore if we have some question from our virtual visitors. So, for example, I can see that we have and someone coming from Florida. Um, I think I think a person also asked about the dust, but I think I already answered that when I was explaining about the cleaning using the carbon dioxide. You see, um, yeah, some person is mentioning that yeah, it's all upside down from northern observers. That's correct. We have everything upside down. Um, and someone is also mentioning that we have a very beautiful night sky, of course, and this person is mentioning the light pollution. Yeah, so by the way, with this comment, I want to mention that light pollution is a problem for astronomy everywhere, not only near Paranal. I mean, people from urban places, uh, they cannot look at the sky. I mean, they cannot look at the stars in the same way like a person who is in the Atacama Desert, of course. But even from Paranal, even from dark places, we have the constant threat of light pollution from distant cities. So that's why in Chile, for example, we have some regulations to prevent light pollution in the surroundings. So it's very, very important to keep the light pollution away because this is the most important, let's say, natural heritage. And that's why at this moment, the top places for astronomy are like, Hawaii, for example, the Canary Islands in Spain, and the north of Chile. So in order to preserve this situation, things like that, we need to keep light pollution away, of course. Um, so okay, so I think we don't have more questions so far. So I think now I am in conditions to say goodbye. And of course, I want to thank you very much to all of you for going for coming to watch this virtual experience. And I also want to remind you that all this visit information and pictures are all available on the ESO website. Okay, so you can take your time to know more about ESO and all the observatories. So, okay, I hope you like this virtual experience and please stay updated in the ESO social networks to know when we will have the next virtual tour. We have virtual tours in Spanish and English, Paranal and La Silla. Okay, so I hope you can come again if you want to know more about the next virtual tour. And on behalf of Piso, well, of course, I want to say thank you again for your presence, and I hope to see you again in another opportunity. Thank you very much, and goodbye.